Statistical Papers Journal. So these are the outline of this presentation. And so entropy, I think you all know that entropy is a measure of uncertainty defined by Salmon. So I will be mainly talking about extropy. So extropy may be new to some of the people because extropy first time defined by lab in 2015 only. So it is just the complement of entropy. So extropy and entropy both measure uncertainty involved in a random variable or in a distribution. So these are some motivation behind this. So because since time is less, so this is a definition of entropy defined by Saylor in 1948. For the discrete random variable, we define it like this. So minus summation of pi log pi, where pi is the PMF. And for the continuous random variable, we define it integral of fx log fx minus. It's the question of minus log fx, you can say. So here we can simply notice that in case of discrete, it is summation. In case of continuous, it is integration. PMF is replaced by PDF. But in case of extropy, so if I come to extropy, this is the definition of extropy defined by lab, and it is just given in 2015. This is very recent. So if you compare, so here it was entropy was pi log pi minus, and they just replaced PMF by 1 minus PMF. But in case of continuous, you may surprise what happened. So like here it is fx. So why didn't we replace fx as 1 minus fx? I mean, they tried actually. So when in the paper they explain that, so like extropy for the continuous random variable comes in this form. It is why because if we replace PDF by 1 minus PDF, so what will happen? Log 1 minus PDF will not be defined because PDF may take value more than 1. For example, in form 0 half. So that's why this term will be not defined. And then they do Taylor series expansion and then some approximation. And after the proof is given in the book, in the paper that lab 2015, they define that after some shifting of. Then so extropy for the discrete random variable is defined like this by lab, and extropy for the continuous random variable is defined like this. So minus half integration fs square x dx. So we can say expectation of fx upon 2 minus fx upon 2. So since log is removed from this, so it makes some convenience. So for the entropy or continuous random variable is this, and the extropy for the continuous random variable is this. So there are a lot of advantages in extropy. And recently in 2023, recently a paper by I think Thomas. So they have shown that for the mixed distribution we have closed form of extropy, but we don't have for entropy. So there is a recent paper. Yes, this one, the first one, Thomas et al. 2023. They gave that the one advantage of extropy as compared to the other method is that it takes an expression for the finite mixed distribution, while no such expression is available for the closed form of entropy. And this is given in the Thomas et al. This was published in So I come to the point rightly. So what we have done in this paper, we have given some characterization of continuous symmetric distribution using extropy method. So record value is defined in the paper Hassanullah and Arnold. So it is the consecutive maxima, you can see. This is the definition of record values. So we know order statistics, we have all know order statistics. This is some modification in the order statistics, define record values. So what we will be using? So I will be using just this expression. So in the paper Arnold and Hassanullah, they have given the expression for the PDF of nth upper record value and nth lower record value. PDF and CPF of upper and lower record value are given there in the paper. So we will be using this in our characterization. And the next one, this one is the nth upper k record value and nth lower k record value. So this is the PDF and CDF of nth upper k record value and nth lower k record value. These are given in that paper only. CF at k plus x equal to 1. Then obviously in case of k must be the mean of the distribution it exists. So it means if any distribution is symmetric, it must be symmetric about its mean only. And the example of some symmetric distributions are given here. We all know that. So this is just empirical distribution function. If you have random sample, then based on order statistics, we find the empirical distribution function. So Amadi in 2021, so this was a reference paper for us. So they have given many characterization of continuous symmetric distribution using entropy measure. So they have done work on entropy. They have used entropy, and then based on k records, they have given many characterization of entropy. So based on that, we try to find some similar characterization using extropy. And they have used like cumulative residual entropy, past entropy, Shannon entropy, linear entropy, totalist entropy, and some carriage inaccuracy entropy measure actually. And they proved that the equality of upper and lower k records is a characteristic property of continuous symmetric distributions. So for the reference people can see. So they have worked mainly on entropy measure. So what I will be working on extropy measure. Q in 2017 gave this characterization. So they gave that we have random sample x1, x2, xn from a distribution x or a sample distribution random variable x population x has symmetric distribution if and only. So J is the notation for extropy. So extropy of first order statistics is equal to extropy of nth order statistics. And based on this characterization, this Noghavi and Jafri in 2022, they have given test of symmetry based on this theorem. So they have used this theorem they made a test of symmetry. They gave a estimator, and then based on that we can test symmetry of the data. Then in following year, Geom in 2021, they have proved that X has a symmetric distribution of mean mu if and only extropy of kth upper record value is equal to extropy of lower k record value. And based on in the same paper, based on this theorem, they have gave test of symmetry. Then continue this work. Jose and Chaudhary in 2022, they gave this theorem that we have a sequence of IV unavailable. Then under this condition, X has symmetric distribution if and only the extropy of nth upper k record value is equal to extropy of lower k record value. In the same paper again, using this theorem, they have given test of symmetry. So they have given estimators and then they tested symmetry for the data.
So you are due to the record points.
Yes, sir.
Record points, right?
Record. Yes, sir. So here we will be providing some characterization for the symmetric distribution based on extropy. So this is the theorem. Actually, this lemma is used mainly to prove our theorem. So in the theorems, we have used this lemma to prove theorems. So proof involves using this lemma. So it says that X is a continuous random variable with PDF fx and CDF capital Fx. Then small fx of capital F inverse u is equal to small fx of capital F inverse 1 minus u. These two are equal for almost all u belongs to 0 to half if and only distribution is symmetric of k. And in fact, I say if it is symmetric of k, k must be the mean. So, and here we define the class of distribution that satisfies this condition. So C denotes the class of all continuous distributions that satisfy this condition, like fx of f inverse 1 minus u is more than or less than equal to or less than equal to fx of f inverse u. And if both are equal, then distribution is symmetric. Now here some terminology will be defined that. So cumulative residual extropy will be defined like this. So minus half integration of f bar square x. So f is the CDF capital F bar is the 1 minus CDF or survival function. And then cumulative past extropy. So here you can simply note that in the definition of extropy, PDF is replaced by f bar in the first one, and the second one PDF is replaced by CDF. So the definition, this is given is, so random variable x is symmetric if and only if cumulative residual entropy of x is equal to cumulative past entropy of x. This is the first theorem, and similarly, so next result is if distribution is symmetric, then n is the nth record value. They are nth lower k record value, un k is the nth upper k record value. So they are similar theorem, just based on x. Here it is x, and then we observe the same will happen for the cumulative past entropy of nth lower k record value is equal to cumulative residual entropy of nth upper k record value. Now the next term is generalized cumulative past entropy and generalized cumulative residual entropy. So in the last definition, here it is power is 2. So in place of 2, it is m is taken. So this term is defined as generalized cumulative past entropy, generalized cumulative residual entropy. Then using these definitions, we have given this theorem that random variable x is symmetric if and only if the generalized cumulative past entropy of x will be equal to generalized cumulative residual entropy of x. And then same thing for the record values. So again, the same thing will happen for the record values. Now, Carey's in 1961 introduced measure of inaccuracy or Carey's inaccuracy. So we are taking this Carey's inaccuracy entropy measure, the following one. So Carey's inaccuracy entropy measure of xy is minus half fx into fy dx, and we can simply observe that if pf of x and y are same, then it reduces to entropy only. If fx of x and f of y both are equal, then it will be just entropy only. So using this definition, so we are finding just Carey's inaccuracy entropy measure for the upper nth upper k record value with respect to x and lower nth k record value with respect to x, and both x and y. So when in place of x we are taking upper and lower record values. So then we obtain this theorem that random variable x has symmetric distribution if and only if. So Carey's inaccuracy entropy measure of upper nth. Now k is replaced by 1 because initially we tried for k, but both were not equal. So we have to put k is equal to 1. In the past theorems, you might be seeing that here we are taking k, ln k, un k. But in that theorem, for any general k, it was not coming. So we have to put k is equal to 1. Then we are able to prove this theorem. Then this next term is cumulative residual entropy and cumulative residual entropy inaccuracy and cumulative past entropy inaccuracy measure. So these are definitions. Based on these definitions, so again we are calculating the same thing for the record values. And then this is the theorem corresponding to that definition that x has symmetric distribution if and only if cumulative residual inaccuracy entropy measure is equal to cumulative past inaccuracy measure. There is upper record value, there is lower record value, both are equal. So these are the theorems, and then we are verifying this theorem just using few examples. So for example, first example is power function distribution. The PDF is given like theta is equal to power theta minus 1 and CDF is equal to power theta. So if we calculate fx of f inverse x, this theta u is for this, and fx of f inverse 1 minus u. And since, so we can just observe that. So what we are saying, when can we say this is symmetric? So if theta is equal to 1, then this will reduce to symmetric distribution, and this belongs to class C, obviously. So just we are verifying. So first we are checking whether this belongs to class C or not. So what was class C? Whether f of f inverse u, this quantity is less than equal to this, or this quantity is So we just wanted to verify whether our theorem verifies this. So then here we are just calculating difference of cumulative residual extropy and cumulative past extropy. So just delta 1 is the difference of that, and we have shown in the theorem that x is symmetric if and only if delta 1 will be 0 there. So just we are verifying. So delta 1 we have calculated this, and delta 1 is 0 if and only if theta is equal to 1, and that we have seen there also. When theta is 1, this is symmetric. Same thing, then this example Pareto distribution we verified that it belongs to class C, and then this is symmetric. Oh, so here it is saying that here we can see that fx of, so this will never be equal actually. These two quantity will never be equal for any theta, and that means that this distribution is not symmetric. It belongs to class C, but it is not symmetric. And our theorems, so I'm using theorem 2.9. So delta 2 should be 0 if it is symmetric, but it will never be 0. It will always be positive. Delta 2 is always positive for all theta more than 0. So means this distribution is not symmetric. So this distribution will not be symmetric. Again, exponential distribution. So this is not symmetric again. So this will, our delta 3 will not be 0. This is positive. Yes. Next is uniform distribution. So it is symmetric. So obviously it will be equal. And next is standard normal. And then, so in the review process, they asked us to give one application of that. So it is published paper already. So in the review, they asked us to give a proof application. So what we did, we can use any one of the theorem given in the paper to give a test of symmetry. So we used actually carriage inaccuracy extropy. I think this is if I need to use. So what we are doing, just carriage inaccuracy extropy measure of ULK of x and LLK of x. And since we have given theorem that x is symmetric if and only if these two will be equal. So what we are taking, the difference of that two we are taking as a test statistics. So we are giving estimator, and then using that estimator we will be testing of symmetry. We will be giving a test of symmetry. So that delta n1 is a test statistics for us. And so Reggie said in 1976 they have given an idea to find an estimator. So what they did, they just suggested that replace CDF by empirical distribution function, empirical CDF, and then the term like, so we are using that idea given by Reggie said in 1976, and we got that the estimator of the delta n1, or this is the estimator of test statistics. This is the estimator we will be using. So here it involves some small m, you can note that. So m is window size, and that will take value between n by 2, 1 to n by 2. Yes. So now what we did, just we have two data set and we are testing it. So corresponding to the first data set we have finished on the paper, and then what we have obtained. So this is data set 1. So corresponding to this data set, the test statistics has a value 0.035, and the p value we are getting is 0.5275. So p value 0.5275. If we are testing at 5% level of significance, so p value is sufficiently large than 5%. So we will not be able to reject H naught, and this means the delta is symmetric actually. And same thing for the 3 data set we have done. So we have 3 data sets. We have applied data set to our test, and the corresponding p value are given. The first data set gives p value 52% across. Second data set gives 0.00, less than 1%. So means second data set is not symmetric and first is not symmetric. Because in the second data set p value is less than 5% if you are taking and testing at 5% level of significance. Oh, sorry. So in that case, second data set is not symmetric, and that's also. Oh, sorry. See here, this is the references that we used. Actually, this was a part of PhD presentation, so that's the same thing they used.
Can you go to page 13?
Yes,
Page
okay.
19.